Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Yeah, you can. Okay, yeah, you can find it on Google. It's a real term. Do I need to switch something on, do you think, or? Okay. Okay. Right, so thank you, Galen. So yes, the title of this talk will be Scalability and Extensibility in the Denali Virtual Machine Monitor. And as Galen so artfully pointed out, I'm Andrew Whitaker from the University of Washington. So before I dive into the details of my work, I'd sort of like to give you a little bit of context on operating systems in general and how operating systems research is changing over time. I think for most of the history of our field, we've been very concerned with performance bottlenecks. How do I make this web server go faster, or how do I make this application have a faster response time? And what we're finding as systems people and application people is that very often performance is not the dominant factor driving the evolution of systems. For the simple fact that hardware has gotten fast enough from Moore's law that very often the systems we have are simply fast enough. We don't have to super optimize the system software to squeeze every last inch of performance out of the system. On the other hand, there's a set of very pressing problems that we've traditionally neglected, problems like correctness and security, reliability, and maintainability. So sort of a set of challenges I'll group under this heading of robustness, right? And so one thing we might think of doing is looking at how we can take sort of this, maybe not a surplus, but an abundance of CPU cycles and performance and sort of trade that for some of these properties that we want to try to achieve. So robustness properties like correctness and security. So maybe another way of thinking about this is even if we as systems people do nothing, the systems will continue to get faster. But unless we as systems people do something, issues like correctness and security and reliability will languish or very likely get worse. Okay. So that's sort of where I'm coming from and the context for the research I've done. What I'll talk about in this talk is my dissertation research, where I look at sort of one particular way to achieve some of these robustness properties. And the approach I'm going to talk about is this idea, which is really pretty simple. What we're going to do is instead of running the operating system directly on the physical hardware, we're going to add a virtual hardware software layer between the physical hardware and the operating system, right? So in general, if you think about virtualization and virtual things, the goal is never to make the system faster, right? So virtual memory is not faster than physical memory. Virtual functions are not faster than physical functions, etc. Right? So performance is not the goal, but very often the goal is to gain some level of flexibility, or maybe just a layer of indirection between some interface and the implementation of that interface. And I'll argue in this talk that this layer of indirection that virtual hardware gives us can achieve these robustness properties in some cases, like security and reliability and maintainability. Okay, so this is the point in the talk where I have to come clean and say that this idea of inserting a virtual hardware layer is not my idea. In fact, this is a very old idea dating back to the 1960s. It's a concept called a virtual machine monitor. And like many things in computer science, it was proposed by IBM in the late 1960s. Basically, what they were after at this stage was some system that allowed them to execute multiple, what we'll call guest operating systems on a single machine. Right? So in this case, we're running Windows and Linux on a single piece of hardware, a single PC, if you will. And as I said, this is a very old technology, but recently we've seen a rebirth in popularity of virtual machine systems. So in industry, we have VMware and Microsoft's virtual PC, virtual server. IBM is still in business doing ZVM and other products. And on the academic side, we have the Denali work, which I'll talk about today, and the Zen virtual machine monitor from Cambridge. Okay. So virtual machines are sort of a hot area. Everybody's interested in virtualization. What I'm going to focus on today is our work, or my work, on the Denali virtual machine monitor. And at a high level, we've had a pretty simple objective, which is we're trying to apply virtual machines to as many problems as possible, or as many problems as it makes sense to do so. So we're trying to expand the problem space for virtual machine monitors. And the way we'll go about this is to imbue our virtual machine monitor with two new properties, or two new goals, that virtual machine systems have traditionally not had. And right now, I'll just mention what these two properties are, and in the next two slides, I'll sort of expand on them and motivate them and give you a description of why I think they're important. So the first property we want in our virtual machine monitor is scalability. We want the ability to run many virtual machines on a single physical machine. And for some technical reasons, we'll get into some reasons why traditional virtual machine monitors have not or cannot achieve this goal. So running many virtual machines is one goal. A second goal that I'll look at today is extensibility. And what I mean here is we want the ability to add new functionality to a virtual machine monitor easily. That is, without rewriting all of the internals of the existing virtual machine monitor. So you can think of this by analogy with how operating systems work. So if you take an operating system like BSD, that supports multiple file system implementations, right? So you have sort of a default file system like the fast file system, but you can also have other file system implementations like NFS and the log structured file system and a cryptographic file system and a versioning file system, et cetera, right? And you can add this new functionality without rewriting the core operating system. And I'll argue that this is a valuable and useful property that we want to have inside of a virtual machine monitor. Okay, so the goal, as I said, is to expand the problem space for virtual machine monitors. Let me give you a better description of the sort of problems I think we can solve once we have these new goals of scalability and extensibility in place, right? So when we started off looking at virtual machine systems, we were very interested in this problem of partitioning a physical server across a set of server applications, or maybe a rent-a-server scenario is maybe another way to think about this, right? So you might have a group of researchers or developers who want to share a physical machine across a set of servers, a web server, a game server, an overlay router, or something that's probing the network with trace routes or pings, and we want these to coexist on a single piece of hardware. Maybe to make this more interesting, you can think of these being untrusted applications. So anybody on the internet can publish one of these servers and have it exist inside of the infrastructure, right? And so virtual machine monitors are a nice system substrate for this because they provide strong isolation between these services. That is, we don't have to trust the security of a monolithic operating system underneath us. And in addition, everybody can choose their own operating systems and libraries and applications, right? So it's just like having your own physical server, only you don't need the dedicated machine. A problem here, though, is that traditional virtual machine monitors are not scalable. And if anybody can publish one of these services into the infrastructure, it's very likely that we're going to end up with a large number of unpopular servers, right? So if any of us could publish some new internet service, very likely each of those services individually would not be extremely popular or would not require a large amount of CPU load. And so being able to support a large number of these would really sort of lower the barrier to entry for carving off a piece of a service or a piece of a physical server. Well, we'll start to look at we'll look at what we can sort of achieve in a little bit later. But I don't know, maybe hundreds or upwards of 1,000 or something like that. I guess the goal for scalability is that we should be able to, that is, the physical machine has some raw capability in terms of requests per second or whatever your workload of interest is. And we want to be able to sort of partition that up arbitrarily across a set of virtual machines. So we're not trying to increase the size of the pie. We're just trying to slice the pie up in an arbitrary way. So we can create protection domains without affecting the overall throughput of the system. So, but to give you a concrete number, we've sort of looked at hundreds or maybe upwards of about 1,000. And at some point, you'll run out of some hardware resource, often memory or something like that. That's sort of the scale we're playing at. OK, so that was sort of the reason we became interested in scalability initially. And since that time, we've sort of, people are starting to look at other ways that a scalable virtual machine monitor might be interesting. Right? So if you want to run large-scale network simulations with hundreds or thousands of nodes, a virtual machine monitor is a practical way to get there. Something else that's been proposed is to use virtual machine monitors for honeypots. A honeypot is just a system that's designed to be broken into. And if you can run many software configurations, that means you sort of cast a wider net in the range of security vulnerabilities that you can capture, right? So Windows with Service Pack 2 is different than Windows without Service Pack 2. Linux 2.4 is different than Linux 2.6, et cetera, right? So if you can run many software configurations, that's more potential security vulnerabilities that you can capture, okay? So scalability is one property we're very interested in our virtual machine monitor. And really the contribution that I've made in this area is to build a virtual machine monitor with no artificial scaling bottlenecks. And that's kind of what I just said in response to your question. So we don't want the system layer, the operating system, the virtual machine monitor, to limit the scalability of the system. So you should be able to subdivide the workload across an arbitrary set of virtual machines. Okay. The second property that we're interested in is extensibility. And this is a very sort of different idea. Instead of running a large number of virtual machines, in this case, we're going to run a small number, maybe just one, but we're going to use the virtual machine monitor as a layer of indirection for adding some new functionality, right? So people often say you can solve any problem with a layer of indirection. And what I've listed here are a whole set of research problems and solutions that have looked at how you can use virtual hardware, virtual machine monitors, to add some new functionality beneath an operating system and set of applications. So one thing that's very natural to do is to implement a migration primitive inside of a virtual machine monitor. So we want to pick up and move a virtual machine from one physical machine onto a different physical machine. Similarly, you can add intrusion detection, fault tolerance, system replay, system administration services, etc. There's a couple of reasons that you want to do this inside of a virtual machine instead of a traditional operating system. One reason is that the abstractions exposed by a virtual machine monitor are much simpler and lightweight compared to an operating system. So if you think of what it would take to do process migration, you have to extract all of the process state, including file descriptors, cached file system buffer cache blocks, TCP/IP state, socket buffers, and the like, process ID namespaces, all of these things that you have to worry about that are associated with the process abstraction. Because a virtual machine is so simple, it's sort of pinned to the hardware level of abstraction, it's much easier to extract the state from the system. It's just memory state and disk state and the CPU registers are all we need to do to migrate a virtual machine across the network to a different physical machine. Okay, so there's two goals that we're after, scalability and extensibility in our virtual machine monitor. And, sorry. So there's two goals we're interested in our virtual machine monitor, scalability and extensibility. And in the remainder of this talk, I'll that's sort of the two main themes, and the outline of this talk will revolve around those two goals. The first part will be achieving scalability, and then we'll look at achieving extensibility in the second part. What I'll do first is present a little more background on virtual machine monitors and sort of distinguish them from similar ideas like simulators and emulators and the like. And then after the core of the material has been presented, I'll wrap up with some conclusions and future work. Okay, so just to go back in time a little bit, as I said, virtual machine monitors are a very old idea. These were conceived by IBM in the late 1960s, and they were popularized by the VM370 system in about 1972. Okay, so virtual machine monitors turned out to be the right solution for a whole set of problems that IBM was facing. One problem was simply IBM didn't have enough machines, enough cycles to debug their own operating systems, right? So if you've read the mythical Man month, this is sort of the era when all this was happening. So very complex operating systems, very bad software engineering practice in many ways. And so obviously there was a lot of debugging work to be done, and the machines were very expensive, even for IBM. So the ability to partition a physical machine across a set of operating system developers was a big win. Something else that VM370 was useful for was time sharing. So instead of using a system like Unix or Multics, you could give each user their own personal virtual machine, in some sense sort of anticipating the development of personal computers in some way. And finally, of course, you can run multiple operating systems on a single physical machine, and we still do this today, running Linux and Windows on a single machine. For IBM, this is very useful because they were still doing sort of batch-style applications in conjunction with sort of newfangled time-sharing systems or interactive applications. Okay. So there was a set of goals that grew out of these, this time and grew out of the application demands of this era. One goal the systems were after at this time was efficiency. So, and what I mean here roughly is we want the ability to run real workloads inside of a virtual machine monitor. So by running on virtual hardware, it's never going to be as fast as if we were running on physical hardware, but we don't want the system to run, say, thousands or tens of thousands of times slower like we would inside of an architectural simulator, for example. Okay. So maybe a 20 or 30% slowdown is tolerable, but 1,000 or 10,000 is certainly not tolerable. In addition, we want strong isolation between virtual machines, and what I roughly mean here is that virtual machine actions are contained or quarantined inside of a virtual machine. So one virtual machine shouldn't be able to tamper with another virtual machine or the underlying virtual machine monitor. And a third goal is that we want to faithfully emulate the underlying physical hardware architecture. And so this sort of grows out of the goal of running unmodified guest operating systems on top of the virtual machine monitor for goals like operating system debugging. So if we want to debug the operating system, we need a virtual architecture that precisely matches the underlying physical architecture. Okay, let me say a little bit about how these systems have traditionally been implemented. As I said, there's sort of a set of goals here which might be conflicting. So we want to have performance, but we also want to have isolation and faithful hardware emulation. And the way that we achieve all of these is to distinguish between two types of instructions in the instruction set architecture. Okay. So most of the instructions are what I will call normal instructions. And these are instructions that we can directly execute on the native CPU without sacrificing isolation or faithful hardware emulation. So roughly speaking, normal instructions are compiler instructions. Any instruction that a compiler would emit, like a load, a store, an add, subtract, can directly execute on the physical hardware without compromising the safety of the system. On the other hand, there's a small set of privileged instructions that have to be trapped and emulated by the virtual machine monitor. So for example, the virtual machine should not be able to execute the halt instruction and terminate the entire physical machine. That would clearly be bad. Also tampering with physical I/O devices or manipulating the physical MMU. All of these could compromise either isolation or hardware emulation. And so we have to trap and emulate these instructions in software inside of the virtual machine monitor. Okay, let me switch now to talking about the Denali virtual machine monitor. Let me just give you a little bit of background on the scope of the project and where it stands. So Denali is an x86 virtual machine monitor that's been in development for about the past 4 years at the University of Washington. The system is fairly simple for an operating system. It's about 26,000 lines of source code that runs in kernel mode, and also 15,000 lines of virtual machine monitor code that runs inside of extension, or that runs this extension code to add services like migration and intrusion detection. Let me just say that 26,000 lines is maybe a little bit underestimates the amount of work we've actually done, because we've incorporated a large amount of device drivers and kernel support code. And so there's some fairly significant software engineering challenges that go well beyond that 26,000 lines. So at a high level, the goals of Denali are we want to retain the good aspects of virtual machine monitors. So we want to have the efficiency and isolation and legacy operating system support that traditional virtual machine monitors have had. But at the same time, we want to add scalability and extensibility to sort of push the boundaries of what virtual machine systems can do. So in the next sections of the talk, I will discuss how we achieve scalability and extensibility in the Denali virtual machine monitor. Okay. So let me start off by defining scalability, and I'm going to define this in terms of an aggregate performance metric. Okay. So for some given workload, let's say a web server workload for the sake of concreteness, what we're going to do is sum across the performance of all of those virtual machines, giving us the aggregate performance. And if the system is scalable, we want the aggregate performance not to decay simply by adding more virtual machines to the system. So if we were to sort of contrast this with operating system terminology, this would be like increasing the number of processes or threads that are running inside of a web server. So similarly, we don't want the performance of the system to decay simply by adding more virtual machines to the system. So we want to be able to create very small protection domains without compromising the performance of the system. So a flat line in this section will be a good result. We want scalable performance as we increase the number of virtual machines. Okay. So I'll be primarily concerned with throughput in this section. So yeah, so that's a good question. So it will be bandwidth or throughput-like metrics. So clearly, yeah, so response time is going to be more strongly affected by context switching and by adding more execution context to the system. So that's another metric you could think of optimizing for, but that's not something we've spent a lot of time on. Okay. So what we found in our work is that there's a couple of barriers to scalability that exist inside of traditional virtual machine monitors. And so if you sort of think of what the virtual machine monitor does, its role or task in some sense is to fake out the physical hardware. Right? So I'm going to take what we normally think of as a physical machine and try to emulate that in software so that multiple virtual machines can share that same physical machine. Right? So its task is to fake out the hardware. And as we add more and more virtual machines to the system, this task of faking out the hardware becomes increasingly difficult because each virtual machine is really only running 1/n of the time. And we'll talk about some specific scenarios and ways that that the ability to emulate hardware breaks down as we add more virtual machines to the system. There's sort of a flip side to this problem, which is that each guest operating system assumes that it owns the physical processor, right? So that's the way it's been coded. That's the assumption that these systems are typically built to. And so each guest operating system will use resources in a way. Mental note, turn off phone. Each guest operating system will use resources in a way that may not be globally optimal, or it may make local assumptions that do not result in good aggregate behavior. Okay. So before I talk about sort of some specific barriers to scalability, let me talk about our approach to dealing with these scalability bottlenecks. And the approach we take is an idea called para-virtualization that Galen mentioned. And really, this is sort of a long name for a very simple idea. Para-virtualization is basically us throwing our hands up in the air. It's me turning off my phone. Okay. Yeah, so para-virtual, so as I said, so it's very difficult to virtualize the physical hardware architecture. And so para-virtualization is basically us throwing our hands in the air and saying, instead of trying to virtualize the physical hardware architecture, which is difficult, let's change this virtual hardware architecture to reflect the fact that we're running in a virtual machine environment. and therefore it will be easier and more natural to virtualize this architecture, right? So we're going to expose a virtual architecture that is in some sense virtualization aware. So all of the difficulties we had in emulating the physical hardware architecture, we can deal with and improve upon by defining a virtual architecture that is more naturally aligned to the needs of virtualization. And I'll be more concrete about what I mean by that in a couple of slides. Yeah. So that's a great question. So I think the answer to that is, I'll discuss the answer to that in the next slide. Okay. It's a great question. So there's a couple of it. So we'll get to the next slide in about 20 seconds. So there's a couple of implications to notice here. So first of all, by changing the virtual architecture, I'll argue that Denali can scale to many virtual machines, and you'll just have to trust me on that for the time being. And at the same time, we're at the very least going to need to port guest operating systems to run on top of our modified virtual architecture, right? Okay. So let's sort of discuss this issue of what it means to port an operating system and sort of the implications of that, right? So one of the key benefits of virtual machine monitors that I argued initially is that they can support legacy operating systems like Linux and Windows and BSD without modifications, right? And now that we've changed the interface between the hardware and the operating system, that sort of breaks away at that, or sort of knocks that property down. And in the worst case, we might have to rewrite the complete operating system to run on top of our new virtual architecture, right? And so sort of the insight that makes this possible, I think, is that modern operating systems are designed to be portable, right? So at the lowest layer, they have this hardware abstraction layer that is designed to sort of shield the core of the operating system, sort of system calls and the file system and TCP/IP from the details of the underlying physical hardware architecture, right? So based on the fact that operating systems are designed to be portable, we can sort of use this hardware abstraction layer as sort of a degree of freedom. So anything that's defined within this hardware abstraction layer, we can use that as sort of a way of keeping the core of the operating system stable, so we can still run Windows and Linux applications, but while giving us the freedom to sort of modify the virtual hardware architecture. And maybe I can make an even stronger statement, which is that we can sort of design the virtual hardware architecture and this hardware abstraction layer at the same time. So these can sort of be co-designed. So this is a very backwards way of designing a system. Normally, as operating system people, we're given a piece of hardware, and we we design an operating system to run on that piece of hardware. Now we have the option of looking at how the operating system is defined and pushing that down into the implementation of the hardware abstraction, sort of the interface of the hardware abstractions, right? So we can sort of modify a piece of the operating system and a piece of the hardware in conjunction, and sort of the ability to modify both of these pieces at the same time will be pretty powerful. And I'll talk about how we exploit that in the next couple of slides. Before I do, let's pick up this point of sort of how this differs from a process abstraction, because I think that's actually pretty deep and a lot of what's going on here. So the question, if you missed it, was once you've started changing the hardware architecture, the architecture that exists between the operating system and the physical hardware, at some level, right, if you make enough modifications, you could end up with a system that has a bloated or larger API, and that is as soon as you've changed the architecture in some way, then how do you know you haven't changed it in a way that fundamentally changes the virtual machine-ness, or makes it more like a process and a monolithic operating system and less like a traditional virtual machine system? And I think our answer to that would be that by confining the changes to the hardware abstraction layer in this way, all of our virtual hardware features are sort of like physical hardware features in the sense that they're captured by this definition of abstract hardware. So there's this software interface that is designed to be a small shim over the physical hardware. And by designing our virtual hardware to be incorporated within that shim, it's perhaps arguable that our virtual hardware is sufficiently like physical hardware that we retain the properties of virtual machine systems. But I totally agree, it's a slippery slope. What's that? I totally.
The hardware abstraction layer is defining and restricting it. An argument that normally gets advanced by people with virtual machine software, which you haven't presented here, is one of the reasons that virtual machines are good is that operating systems tend to have holes in them, and because the interface here is so simple, it's unlikely that we're going to be able to compromise the virtual machine layer and use that to get at the other machines that are running the system. The isolation.
Yeah.
It's the justification for isolation.
Yes.
And the danger as you start putting a richer interface in there, you start building coding drivers and all this stuff that people do, is that you no longer have as strong an argument that there isn't a holdover. And the truth is, processes are a lot easier to program than a lot hardware is. So there's some pressure that's pushing you in that direction.
Right.
And so I always ask everybody.
No, it's a great point, and I totally agree. And I do think, if you look at sort of the interface that the hardware, the hardware abstraction layer sort of differs a little bit across operating systems, but it's not very abstract. The sort of semantic distance between the physical hardware and what is exposed by the virtual or by the hardware abstraction layer is semantically pretty small. There's nothing, the disk device driver interface is not fundamentally different than the physical disk interface. A little bit cleaner, but not a radically, there's a much smaller gap between that and the file system, I'd say. And so it's a squishy argument, but I think that's sort of what we've tried to adhere to in changing the architecture. But I completely agree with the sentiment, and I think that's why this is a little bit of a controversial idea, but we'll just have to go with it. So.
You're right that you actually need to do this in a room like your work. I'm not disagreeing with that at all. Once you start it down, right. And the reason that it's dangerous is that it's really hard to tell at what point you use the isolation problem. If you tell that accurately, then we can find all the problems that are in interfaces that have down processes for both fine.
Right.
Evidence says that you haven't done it.
Right. And there's sort of a deeper issue here, which is that there's no way to measure isolation. That is, there's no benchmark for how sound your isolation mechanism or any of these things are all of these things are sort of fuzzy notions to begin with. And so sort of intuitively, I sense that this laptop is distinct from that monolithic looking huge Dell there, right? And so that there's some isolation I get from that level of separation. And virtual machines sort of seems like it's approximating that, much more so than processes. But once you start to muddy the water, I agree, it's a slippery slope, and I'll just leave it at that. Okay, so let's look at a couple of changes. So let's make this all much more concrete and look at a couple of changes we made to the virtual architecture, and then you can all sort of judge how far down the slippery slope we've gone, right? Okay. So one of the first things we looked at are timers and timer interrupts and how they have to be handled differently inside of our virtual hardware architecture. So just to give you a little bit of background, in a normal operating system running on physical hardware, it uses timer ticks from a programmable interval timer to demark the passage of time, right? So timer ticks will come in, say, every millisecond or every 10 milliseconds, and that's how we'll know that some period of time has passed. Okay. Now you can maybe start to see the problem here. In a virtual machine context, each virtual machine is running only 1/n of the time, right? So in this scenario, each virtual machine is only going to see 1/4 of the timer interrupts, right? Okay. And as a result, it's going to have sort of a skewed view of time. Its view of time is only going to advance 1/4 as fast as the global view of time. Okay. So maybe your first response to this would be simply to do nothing. That is, just let the virtual machines see their own individual time slice and sort of the virtual view of time as opposed to the physical view or the wall clock view of time. But very often we do care about the passage of physical time, right? So for example, TCP retransmission timers are fundamentally bound by real-time considerations, right? It says in RFC 789 or wherever it's defined that TCP retransmission timers need to fire at a certain time, and that's dictated by real-time constraints. And so we need some version of real-time to percolate up into our virtual machines, okay? So maybe the second thing we might think of would be to raise this huge batch of timer interrupts when the virtual machine begins its normal scheduler quantum. This has a couple of drawbacks. First, this would incur a large amount of overhead if we were to deliver 8 interrupts or however many interrupts we missed in the preceding scheduler quantums. And this is also going to sort of wreak havoc with any internal scheduling that the virtual machine is trying to do. So if you're the process inside of this fourth virtual machine that happens to be running, you're going to be charged a large number of timer ticks and won't be particularly happy about this implementation choice. Okay. So what we do instead in Denali is to fundamentally change the way that timers and the passage of time are indicated in our virtual architecture. So instead of raising a large number of timer tick interrupts, we raise a single interrupt which has different semantics. And this is a context-switched interrupt, which just says, you were context-switched out for some period of time, and I'm not going to tell you how long. You'll have to check this global time counter in order to figure that out. Right? So, hey, you were context-switched out, and if you look at this global time counter, you can see that, in fact, 50 milliseconds have passed, and you need to check any timing-related functionality and trigger that in some way. Yes? Yes.
Why not just use the code frame time equation? So every time it typical amount of time get answered.
Yeah.
What the machine is no upfront, like there are timer interrupts every 4 minutes. Implement there is no enough time by 4 minutes.
So sort of slow down the rate of. I mean, so one problem with that is that
that would solve your TCP problem because it roughly schedule whatever you say.
Right. I mean, so one problem with that is that the granularity of timers is sort of dependent upon the number of things that are running, which is sort of an undesirable property, perhaps. And so, and in particular, the granularity of timers you can expose is, oh, now there's 10 more virtual machines, and so I've lost an order of magnitude in how precise my timers are. And so, but there's really a more fundamental issue, which is that we really have two notions of time here. There's sort of there's sort of wall clock time that's on your watch, and virtual time as seen by the virtual machines, right? And so, and sometimes you care about physical time for TCP retransmission timers. Sometimes you care about virtual time if you're doing your own process scheduling or something like that, right? And so it's really hard to fake out one with the other. You sort of need to understand both and be able to change the guest operating system in some way to know that these two notions of time exist. Yes? Well, that's a great segue to my next slide, so I can pick up with that. You read my mind, or you saw my slide deck. So okay, so idling is actually a very interesting question, and so let's talk about that a little bit. Okay, so really the problem with idle loops in the context of virtual machines is that they're sort of unnecessary, and in the worst case, they waste CPU cycles. Right. So normally, when an operating system doesn't have any useful work to do, it sits in an idle loop and does nothing, waiting for some event to arrive. So maybe waiting for an interrupt to arrive or something like that. Right? In a virtual machines context, this doesn't make sense, right? Because even if our virtual machine has no useful work to do, there may be some other virtual machine that has active computation and can do something useful, right? Okay. And so we need a couple of things, right? First, we need some mechanism for inferring that virtual machine is in fact idle. And that actually exists in most systems, like the idle loop we'll call the halt instruction or something like that, right? But what we don't have is some mechanism to let the virtual machine monitor know how long that virtual machine is going to be idle, right? So if you have a TCP retransmission timer that's set to fire in 70 milliseconds, there's no way for the virtual machine monitor to really know that. So it would have to peek inside your timing data structures, and it requires more knowledge than the virtual machine monitor traditionally has. Yes? Not necessarily, because the interrupt that is, so in the case of something like a TCP retransmission timer, the whole point is that there is no interrupt set to fire. That is, the packet gets lost on the wire, and so some timer needs the, what's that? Yeah, so in the previous, in some sense, what the timer mechanism, and I probably could have explained this more clearly, the timer mechanism is all about turning off the periodic clock. So you don't want to we don't deliver each timer interrupt to each virtual machine. You only see the particular subset that occur when you're running, and then you. Yeah. Yeah. Well, and sometimes it's a lot longer. Yeah. And Yeah. So there's this issue of the timeliness and the degree to which, how expeditiously you can handle the virtual interrupts, right? And so part of that we deal with because we're implementing virtual hardware abstractions. We can sort of implement them in a way that is sort of less timing dependent, right? So, we allocate a new packet buffer with malloc, right? It's not a piece of memory on an ASIC or something like that, right? And so we can sort of design our virtual hardware abstractions with a little more leniency in terms of, you can add more buffering or design the virtual hardware abstractions in a way that are sort of cognizant of the fact that there's this time sharing and multiplexing that's going on. When you do scheduling. The scheduling at the virtual machine monitor level? No, I'm not. Right. So I'm not going to talk a great deal about scheduling. Once you've sort of gotten. That is, at some level, scheduling virtual machines doesn't turn out to be radically different than scheduling processes. Once we've sort of allowed a little more information to pass back and forth across this interface, right? So we know how long, virtual machines are going to be asleep, and so we can wake them up at some point in the future. We know when they're actually doing useful work as opposed to not doing useful work. And so once we've actually passed a little more information across this interface, the scheduling issues are not radically different across virtual machines and processes. So I probably won't say much more about it and just leave it at that unless you have specific questions. It's not something we've invested a huge amount of thought in. Our scheduler is pretty simple. We haven't looked at real-time scheduling constraints or anything like that. You certainly could, but it's just not something we've pushed hard on. Okay. Oh, the knee. So right. Oh, I should actually explain what the graph is instead of just putting it on the screen. So, So what we're doing here, increasing the number of virtual machines. On the y-axis is aggregate served load. It's a web server virtual machine, but that's it's about a 130K size document. And of course, when we add the idle with timeout mechanism, we get back to this nice flat throughput curve. So throughput does not decay as we add more virtual machines. And of course, what has just been pointed out, if we do not have this idle with timeout mechanism, throughput decays pretty rapidly for a small number of virtual machines, and then sort of levels off with this nice knee property. The reason for that, is that virtual machine monitors today have some mechanism for inferring idleness, but it's typically done at a pretty coarse grain granularity. So you might think of something like power management being used to infer that a virtual machine is idle. There's a little bit of speculation here because we don't actually know how most of these systems are proprietary. We don't know how they're implemented. But power management seems like a reasonable guess. And so if a virtual machine goes into power management mode, then you certainly know that it's idle and you don't have to give it the CPU. And so this idle with timeout is meant to reflect that much more coarse-grained idling of the CPU. And the way that we figure that out is if there's any timers that are pending inside of the guest operating system, so any TCP retransmission timer or user mode signal or anything like that, then we conservatively say that the virtual machine monitor would not be able to idle that virtual machine in the absence of this timeout mechanism. So by adding the timeout is really the innovation. It allows you to share the CPU at a much finer granularity. So instead of having to wait till the guest operating system goes into power management mode or some existing. Yeah. So there were. That's right. So there were some instances where we would have to, and you can sort of. There are instances where we had to change the guest operating system to use timers in a different way. So NFS in particular implements like its own TCP, its own network stack. I mean, NFS is sort of an operating system unto itself, and it tries to count timer ticks, and it tries to do its own reliable transmission, and NFS is just its own world. And so we had to peek into a few subsystems. NFS comes to mind, and sort of figure out, oh, that's not really a real timer. That's just sort of NFS doing its own bookkeeping and sort of. Yeah, so there was a little bit of going in and mucking around with some of the details of systems that use timers and distinguishing between, this is some active computation versus bookkeeping that could be delayed and built into the idle mechanism. Okay. Right. So this particular context. So for a lot of these scalability measures, we were running sort of a very lightweight operating system that was sort of directly linked against the application. So we also have sort of NetBSD that works in conjunction with Denali. But for these scalability experiments, we were really trying to push hard on the scalability of the virtual machine monitor. And as a result, we were sort of running a very lightweight, simple web server linked directly against a library operating system. And so that's the particular scenario that we're describing here.
How light are we talking?
In terms of the memory footprint or something like that? Yeah, I think a few megabytes is about the right. Yeah, I think 16 or I don't remember the exact number, but it's a very small footprint operating system. So this particular experiment was sort of our own web server linked against what we would call like a library operating system. So sort of a BSD TCP stack and a threads package and just sort of a set of operating system functionality that was sort of cobbled together from components. And so it's about as light a weight a virtual machine as you could possibly have. Yes. Yeah. It's you can go there. That's fine. Yeah. Right. So we've done some experiments there, and sort of the Zen people have sort of taken a very similar architecture and achieved similar scalability numbers. So I don't have. We've tried to push on this a little bit, but it's they sort of beat us to the punch in having a full-fledged operating system running in some sense. So it's ceased to be research at some point, and what it basically does is change the constant factor in terms of the graphs look roughly the same in that there's some. It's still a flat line in the case that you have idle with timeout and the timer mechanism and these sorts of things. But it's a bigger footprint and more functionality, and so the exact constant factor is different in terms of scalability. I believe we were just running 20 millisecond quantums in this case. Yeah. About right. Yeah, and then actually pretty soon after this, we were running out of memory, started to become the constraint, and it became disk bound pretty quickly. But yeah, I would expect that if you had more memory, I would expect that to be a factor. Right, and so looking at, it all depends on the workload, of course, right? But so looking at sort of internet-like workloads with lots of TCP connections and sockets and these sorts of things, there's a fair bit of idle time simply because you're waiting on the network a lot. There's real latency, and it's just a lot of the time you're just spinning the wheels, especially as you sort of spread the workload out across more virtual machines. So for these sort of internet-like workloads, lots of TCP sockets and these sorts of things, I would expect there to be a fair bit of idleness. If you're sort of chomping on big numbers in the background, of course, then that's a very different scenario.
You scale up the number of in the physical machine design. Can you think of it because you're sort of network limited?
No, so for all of these experiments, we were CPU limited, and so I would expect. If you were network bound, then it really wouldn't matter what we were doing in terms. Well, it would matter less what we were doing in terms of idling or timers or that sort of thing. So for all of these experiments, we were certainly CPU bound, and so I wouldn't expect adding more NICs would fundamentally change that result. Yeah, this was a this was a Pentium 4, about a 1.7 gigahertz, and the document we were serving was about a 130K web documenter or something like that. Yeah. Okay. Mm-hmm. Yes.
How
Why not?
do
Mm-hmm.
When the timer started to lose its sense of reality. All discrepancies being lost in context.
Mm-hmm.
Too dramatic. That makes it
Right. So what we have done is to make, so there is no, we've basically exposed that disjunction between virtual time and physical time. So the operating system knows that it's there. That's why we needed the freedom to be able to change the operating system. So the operating system is not getting confused. It knows what virtual time is and what physical time is. Okay. Yes. Yes. Yeah. Okay. So let me sort of in the interest of time just sort of look ahead and just touch a little bit on sort of the extensibility aspect of the work, and then I will sort of wrap up talking about some of my research interests going forward. So in this part of the talk, this is sort of a very different idea. So in the first part, we were looking at scaling up a virtual machine monitor, running a large number of virtual machines on a single physical machine. And in this part of the talk, what we're really doing is taking a small number of virtual machines, or maybe a single virtual machine, and adding some new functionality inside of the virtual machine monitor that acts on that virtual machine, right? So we can pick up and migrate a virtual machine, add fault tolerance, intrusion detection, et cetera, right? So we're just going to use a virtual machine monitor as a layer of indirection for adding some new functionality to the system, okay? And there's a couple of reasons we'd want to do this inside of a virtual machine monitor. First of all, the virtual machine monitor is just a much simpler operating system. So a virtual machine monitor might have on the order of 10,000 lines of code versus, say, 10 million lines of code for a full-blown operating system. And so any service that we implement is going to be much easier and simpler to realize. And in addition, we have what you might call a whole system perspective inside of a virtual machine monitor. So instead of implementing migration on behalf of a single process, we sort of take a step back and view the whole virtual machine as a complete opaque abstraction. So we can move the operating system, its configuration state, the registry, a suite of running applications, et cetera, right? So we have a different granularity that we can work with, which is often more appropriate to some application domains. Okay. So really, when we started working in this area of extensibility, the state of the art for adding virtual machine services to a system was pretty primitive, right? So what people were largely doing was building a new virtual machine monitor or customizing a virtual machine monitor for each service that they wanted to implement, okay? So if you wanted to build migration, you would customize a system to have a migration virtual machine system, or intrusion detection, or configuration debugging, or whatever, right? There was sort of a lot of systems that were stovepipes without a lot of sort of interaction or collaboration between these different systems. There was a set of implications for this. So one problem is that there was sort of a lot of reinventing the wheel. People were doing a lot of work to get systems to the point where they could do innovative research. There was sort of a lot of grunge work involved with this. So people were expending a large amount of work before they could actually do anything innovative. And this sort of acted as a barrier to entry for new services. So sort of our goal when we came to this problem was to provide a common extensibility platform. We recognized that people were doing a lot of the same things over and over again, and so we wanted to sort of encapsulate these cleanly and provide a sort of a common framework on which people could build. And so hopefully we could take a lot of this grunge work and incorporate that through some clean interfaces. People could build on top of those and allow them to build new services more easily. And sort of in the longer term, you could think of exchanging different components or parts of a virtual machine service, or sort of running a different, two different migration implementations on top of a single virtual machine monitor, or similar sorts of ideas. So in some sense, we just want to raise the level of abstraction for writing new virtual machine services. Okay. So when we began this, we sort of took a look around and looked at what people were doing in terms of writing new virtual machine services. And what we found is that what people were often doing is changing the way that virtual hardware devices were implemented. Okay, so if you want to implement something like intrusion detection, that really reduces to the problem of changing the way that the Ethernet abstraction is implemented. You want to interpose on the flow of packets into or out of the Ethernet and apply some intrusion detection functionality, grepping across the packets to look for intrusion detection vulnerabilities. Similarly, if you want to implement a service like migration, to do that, you need some way to get access to the memory and disk state that are associated with a virtual machine. Okay. So being able to modify or interpose on the virtual hardware abstractions, be they memory or Ethernet or disk, is sort of fundamental to what people are doing when they extend virtual machine monitors. Okay. So to sort of think about how we might build an extensible virtual machine monitor, we sort of took our inspiration from how you might upgrade a physical machine. Okay, so if you were to add a physical disk to a system, how would you go about doing that? So first of all, you might go to the store and buy the disk. So go to Fry's and buy whatever we can, what is a disk these days, like 25 cents per gigabyte or something like that, right? And then you would plug in the disk to the computer. This is fairly obvious, right? But really the insight that makes that possible is that there's a set of bus standards, right? So you have IDE and SCSI and USB and FireWire, all of these things that sort of decouple the physical hardware device from the internals of the computer, right? So you don't fundamentally have to re-architect the machine. You can plug in the device, and there's this common framework that allows communication between the core computer and the new device, okay? So we're going to do a very similar sort of thing in our extensibility mechanism. We're going to expose what we're going to call a virtual hardware bus, and instead of plugging in physical hardware components, we're going to plug in virtual hardware components or software components that are implemented in software and run inside of virtual machines, okay? So let's take a look at what that might look like. So the approach, the name we give this is called hardware interposition, and the basic idea here is that we're going to route I/O events from a parent virtual machine into or from a child virtual machine and into a parent virtual machine. Okay. So what I'm showing here is sort of a conventional virtual machine monitor where the child has a virtual Ethernet abstraction that is implemented inside of the virtual machine monitor. And this is ultimately backed by the physical hardware. Okay. So what we want to do is get to a world where we can implement some new Ethernet functionality inside of a parent virtual machine. So we want to add an intrusion detection module that takes packets in and sends packets out, but applies some intrusion detection functionality to that stream of packets. Okay. So in order to do this, we're going to reroute packets from the child virtual machine into the parent virtual machine through this virtual bus abstraction. And then from that point, the parent can process those packets in any way that it sees fit. It might send those packets over its own virtual Ethernet abstraction inside of the virtual machine monitor, and then out onto the physical hardware and out onto the physical network. Okay, so one of the key advantages of this approach is that we can add new virtual machine functionality inside of, as user mode code inside of a virtual machine. Okay, so we can take advantage of all the normal user mode abstractions. We have libraries, we have the file system, we have TCP/IP sockets. We also gain a level of fault tolerance. So if this intrusion detection module fails, it doesn't bring down the entire system. The downside of this approach is that we've added some overhead to the system. There's a lot more blue lines here than we used to see in the sort of the previous incarnation. And so we're routing events through the virtual machine monitor into the parent and then out onto the wire. And so the overhead of the interposition is clearly going to be higher than in a standard virtual machine system. Let me just show you a little bit about the overhead of this approach and try to argue that it's tolerable in many cases. So what I'm showing here is a Denali with network interposition versus Denali without network interposition. And this is a single NetBSD virtual machine running various workloads, so Apache serving static documents of various sizes, and also a bulk TCP connection where we just open a single socket from a parent virtual machine out onto another physical machine on the network. Okay. And so in each case, we're computing overhead, so a smaller number is a better result in each of these cases. And this is a Denali versus Denali comparison, so Denali with interposition versus Denali without interposition, running on a fairly fast and modern PC at 3.2 gigahertz Pentium 4, a gigabit Ethernet. Okay, so what we can see is that there's sort of a range of overheads ranging from about 31% in the small Apache document case all the way up to about 43% for bulk TCP connections. And the disparity in overheads has a lot to do with the sort of the makeup of the workload. If it's a very system call intensive workload, then that has a relatively minor effect on network interposition has a relatively minor effect on overhead because we're not interposing on system calls. That's obviously going to add less overhead to the system. If it's a very packet intensive workload, which is the case for bulk TCP, we're doing a small number of system calls to send a large amount of data. That's going to have a larger effect on overhead. And so for each packet, we have to first send that into the virtual machine monitor, then into the parent virtual machine, and then out onto the wire. And so that's about a 43% overhead. I'd like to point out, however, that in terms of real numbers, we're still getting fairly reasonable throughput. So Apache with 2K documents, we're still getting 2,200 requests per second. And in terms of bulk TCP throughput, we're still getting 387 megabits per second of throughput. Okay. So in terms of real overhead, even these fairly substantial relative overheads may not matter that much in practice. So a lot of machines don't even have gigabit Ethernet. And so in many cases, 387 megabits would probably be tolerable. Okay.
So in the case where you have, let's say you're trying to do migration and you're trying to do networking simultaneously, you want to have two things on the bus.
Yeah, okay.
I was just wondering, you end up going through one parent, you go through one parent for each of the abstractions on the bus.
Oh, I see. You could do it either way. It's not something we pushed hard on. I mean, I think that is, you could either do it. It's not something we've actually done, and looking in terms of composing different services and layering them together and these sorts of things. Yeah. It's an interesting question. I mean, I think, and people have looked at doing it both ways in terms of running it in separate address spaces or combining it into a single address space for performance. I mean, it might depend on the sort of service you were implementing. I mean, the disk is so much slower than the network that you can sort of get away with multiple address spaces and more copies. Certainly for the network, gigabit network and these sorts of things, the performance overhead would start to stack up. I mean, ideally, you'd sort of have the part of this I didn't talk about was sort of the programmer's view of the system, the sort of API for writing and composing new hardware extensions. So my virtual disk extends baseline virtual disk. And you would hope that at that level, that programmer level abstraction would sort of insulate you. So you could take a single code module and run it in different address spaces or compose it in a single address space, and it wouldn't matter from the programmer's view. Okay, so really the interesting thing about an extensibility platform is what you can do with it. So I'll sort of wrap up here by talking about some of the services we built inside of the extensible version of Denali. So one of the first things we did was implement a migration service. So migration, I should emphasize, is not new at all. Lots of people have done migration with virtual machine monitors. But what's sort of interesting from my perspective is how simple it was to implement inside of Denali. And so really what migration is just some way to pick up and move state associated with a computation across the network, right? And so really what we do in Denali is cleanly expose the state associated with a virtual machine such that you can grab it and get access to it programmatically, right? So you can implement a virtual disk to get access to virtual disk blocks, implement a pager to get access to virtual memory pages, and similarly grab the CPU state. And so really migration just reduces to some mechanism for sending bytes across the wire. And as a result, it's a fairly simple extension that we can build in our system. Intrusion detection was fairly easy to add because we just took an off-the-shelf intrusion detection system, ran that in a parent virtual machine, and routed the child's packets into that parent virtual machine. So we just connected the child's Ethernet to the parent's Ethernet. This is really just a component programming problem of stitching these two virtual machines together, and so we didn't require any source code lines to add that new functionality. There's a set of other extensions that I won't have time to really talk about in any length, sort of copy on write disks, network booting, something, the Chronus tool, which was a paper unto itself that we presented at the last OSDI. And so the takeaway here is that by adding these sort of clean extensibility mechanisms, we're able to add a lot of new services to our virtual machine monitor with relatively little overhead. And in the case of the Chronus tool, that was actually developed and implemented after the baseline extensibility mechanisms were in place. So we have at least one data point that suggests that these extensibility mechanisms and APIs are sort of useful going forward. We were able to build something new that we hadn't thought about when we were designing the base extensibility platform. Yes. So what Chronus is trying to do is basically be a debugger for system administration problems. And so if your registry becomes corrupted, or if you input a configuration file incorrectly, like an Apache configuration file, or you change the permission on some directory that causes some application to fail in an unforeseen way, or you change the firewall policy, Chronus is sort of a debugger that tries to reveal these sorts of system administration or configuration problems. And it does that by trying to reveal when the system transitioned to a failing state. Okay. So if you have this sort of error where the system was working and then the system was not working, you can try to hone in or isolate this failure point. And once you've done that, if you can compare the system state before and after the failure, hopefully that will shed light on the actual cause of the failure. So it was this configuration file that changed, or the firewall policy that changed, or this registry key that changed, or whatever would have you, right? And so what the system does at some level is to do a sort of time travel search across time to try to hone in on this particular pair of states that represent this transition, okay? And we're sort of rebooting virtual machines in the past and doing effectively a binary search to find this transition point relatively quickly. Okay, so that's the. How does it identify a failure? So it reduces. testing. So it doesn't do it's not full diagnosis. It sort of reduces diagnosis to testing. So there's some input to the problem, which is the system is working, system is not working, something that can distinguish between, yeah. And so, yes, you could either give it an oracle or you babysit it or something like that, right? And so in the paper, we sort of argue at least that there's sort of a class of configuration problems that can be detected with fairly simple mechanisms like shell scripts or that sort of thing. And there's a lot of infrastructure sort of in the software engineering community for sort of letting non-sophisticated testers who are often not computer science people or don't have a programming background, for letting people that are sort of less sophisticated build up regression tests or software tests through sort of point and click tools and these sorts of things. And so there's an argument at least that developing tests for correctness is a lot easier than doing full end-to-end diagnosis. But it's sort of a hypothesis that we haven't completely explored. But suffice it to say that at this point, it reduces the problem diagnosis problem to testing, which can be easier in many cases. Okay, so that's sort of the elevator level pitch for Chronus. And it's interesting because for a couple of reasons. First, it uses Denali's extensibility mechanisms. We use what we call a time travel disk. It's just a sexier way of saying logging disk. And then it also uses the para-virtualized architecture to be able to instantiate and boot virtual machines faster than we could on physical hardware. Before I sort of let you go, let me just wrap up with sort of a set of conclusions and just touch on some areas for future work. Okay, so I hope I've convinced you that we can sort of use virtual machine monitors and virtual hardware to address a variety of pressing systems problems. And Denali has improved virtual machine monitors in a couple of key respects. So we've pushed on these areas of scalability and extensibility. We've given up on faithful hardware duplication, but I've argued that that's okay because of the way that modern operating systems have evolved into having this core part, which is distinct from the hardware abstraction layer. And in the end, I just sort of touched on some of the extensions that we've built on top of our extensibility mechanisms, which suggests that the extensibility platform is useful going forward. Yeah, so this was something I was discussing with Galen, which is this idea of changing the virtual hardware architecture is not fundamentally new in the sense that IBM was doing it in the 60s and VMware ESX is doing it now in terms of tweaking the device drivers and these sorts of things. And we play similar sorts of games in Denali. I think what is maybe a little bit different, or really sort of the perspective we're coming at it from is different in the sense that the traditional systems have sort of tried to minimize the delta between the physical hardware and the virtual hardware architecture. And we're sort of saying, let's take the hardware abstraction layer as sort of this degree of freedom in some sense. And so anything that we can sort of realize within that software layer, we will sort of give ourselves carte blanche to explore and modify those. Yeah, because that's part of that layer. Yeah. So it's just sort of taking an idea that people were doing and pushing it to the limit, I think, is how I would describe para-virtualization. Yeah, but sort of a dipping a toe in the water of para-virtualization, and we dove into the pool. It's just a matter of degree. I mean, they had one particular problem with I/O device performance, and we said, let's just look at how we would design the ideal virtual architecture for running virtual machines. So it's just a matter of perspective and pushing harder on the idea than they have. And they're, from their perspective, it's not a win because they're sort of a company, they're trying to ship a product, and so having to radically change not radically, but change the guest operating systems in any way is clearly a lose. And so from a research perspective, we could sort of say, well, let's take this piece of software and sort of, that's going to give us, anything that's in this hardware abstraction layer, we can sort of think about and reconceive and think about how we might do it better if we could change the interface underneath it. Yeah. It's just pushing harder on the idea. No, yeah, it's a great question. Okay, so sort of going forward, I think I'm sort of generally interested in anything that we can do as systems builders that address the needs of end users. And so if you sort of think of how systems have traditionally been built, they're sort of very computer-centric, right? And that we're sort of optimizing for some piece of hardware or right on the bleeding edge of what some piece of hardware can do, right? So time sharing, when people were doing time sharing operating systems, we were just at the cusp of being able to do that. Similarly, when people were doing the Alto and personal computers at Xerox PARC, that was sort of an interesting systems problem because we were right at the cusp of what the hardware can do, right? And so there's still interesting research that can be done in that vein, I think. But very often now we're seeing that the hard problems in terms of what prevents people from getting work done are issues like security and reliability and maintainability and usability, right? And so if you came at systems from a different perspective, if you said resources were infinite or very plentiful, how could we sort of use those resources to achieve some of these other goals? I think that sort of defines my research philosophy to date and my research interests going forward. So just two major problems area that I'm interested in. A lot of the work that's going on here and elsewhere in terms of building better system software, so operating systems and web servers and other sort of system software that's traditionally been very performance intensive. It's been very hand-tuned and written in C to have very good performance, but as a result may have questionable reliability and security. I think this is sort of a major area going forward, is how we can build these systems to be more robust and more secure. And as a systems person, I'm not too wedded to any particular technique. I'm just interested in anything that will work, right? And so certainly using better languages and tools, I think, is a major way to make progress. I've sort of looked at this a little bit by using some work I did in SOSP03 that looked at using a type-safe dialect of C, the Cyclone language, for loading extensions into the BSD kernel. Obviously, there's a lot of work here that's sort of looking at a more complete way to do, to use languages and tools in the operating system, and I look forward to learning more about that. I'm also sort of interested in maybe less, so static tools are certainly a way to make progress. I also think it's worth looking at sort of dynamic analysis and testing and things that look at actual running code and try to infer properties from that or to enforce properties on that code. Very often statically, you sort of run into constraints about completeness versus, what's the other half of completeness? There's that completeness. Yes, soundness and completeness, right? You sort of run into this trade-off between soundness and completeness. I can never remember which one is which, but yeah. I never remember which one is sound and which one is complete, but I just always mention them in tandem, and then I'm safe. So you run into these constraints of soundness and completeness and sort of static tools, and so I think there's actually maybe some interesting things that you could do dynamically, maybe more like software fault isolation or these sorts of things. And so anyway, so really anything that can advance the art in building more robust system software, I think, is interesting. And a lot of system administration issues, I think, are sort of very pressing and interesting as well. And so there's really no silver bullet here, I think, but looking at how we would build self-tuning systems that have fewer configuration knobs, looking at how we can do better problem diagnosis, or just trying to, obviously instead of doing diagnosis, we prefer to prevent configuration outages in the first place. And so if you could sort of proactively monitor the health of the system and recognize when a problem is about to arise, that would be a very interesting thing as well. And I will just leave it at that. So I'll take any questions that you have.
When you're doing intrusion detection,
yes.
Was the parent virtual machine, was it only the network stack that was virtualized through the bus to the client, or was it the entire virtual machine that was virtualized through the client?
So certainly the network stack was, and I don't recall how the disk and swapping functionality were implemented in that case. You could do it either way. Denali allows you to do it either way.
So you can shunt one of them off through the bus into a parent and update it.
Yeah, so for each of the abstractions, there's sort of a default implementation and then a shunted implementation that you can implement in the parent. Very often for the disks, it was just simpler to implement them in terms of the file system, so you could copy them and sort of use normal file system primitives on the disk devices. But there's also, for each abstraction, there's sort of a default. Because that was sort of the way the system evolved, was that there was a default virtual machine monitor abstraction for everything, and then you could, once we added this shunting capability, you could add new implementations. Yeah. I turned this off. I swear I did. God, I even told.
I was going to say, the guy came in and asked you.
I'm losing it.
That's okay.
I'm losing it.
That's the worst you make mistake you make in a day. You're doing pretty
Are you Jeremy?
I am.
Okay.
Good to meet you.
Nice to meet you. I think you're on my schedule at some point.
Yeah, I'm now actually, which is what I wanted to ask about.
Oh.
So,
You and Bill swap? Or
I don't think so. I thought I was a 3. I just wanted to find out if I should.
pull up your schedule.
3.
This is just a prop. It doesn't actually work.
Oh, you just look cool.
Yeah.